Assalamualaikum students. I am back with another lecture of week 3. If you remember, in the last lecture we started chapter number 3 of book Denison, Air Standard Cycles and their analysis, and we started the chapter with the analysis of Otto cycle. What we did, we drove the expressions for thermal efficiency, net work output and mean effective pressure. Then we solved few numericals of the Air Standard Otto cycle. Now we will do the same thing today for the diesel cycle. That is, the learning outcomes of today's lecture are the introduction of diesel cycle. Then we will derive the expressions of thermal efficiency, work output and mean effective pressure of the air standard diesel cycle. Then at the end of the lecture we will do some problem solving, that is we will solve few numericals of the air standard diesel cycle. These are the numerical statement which we will go through little bit later. So as we have studied in week number 1 and week number 2, that in the diesel cycle we have 1 to 2 isentropic compression. In the air standard diesel cycle, 1 to 2 isentropic compression, volume will decrease and pressure will increase. So from bottom dead center the piston travels to top dead center, and from 2 to 3 is the constant pressure heat addition. So pressure will remain constant, volume will increase and the heat will be added in the to the working fluid. Then 3 to 4 is the isentropic expansion, that is the power stroke. Pressure will decrease and volume will increase, and 4 to 1 is constant volume heat rejection, similar to the Otto cycle. So V4 will be equal to V1. Now here V2 will not be equal to V3. Contrary to this thing, P3 will be equal to P2, that is pressure at 3 will be equal to pressure at 2. So P3 will be equal to P2 and volume will increase. So V3 and V2 are not equal. So as you know that when we compress air and we inject fuel, volume will increase during the heat addition process. So the ratio which defines these two parameters, that is the volumes at 3 and 2, it is the cutoff ratio. The ratio between volume after combustion and volume before combustion is cutoff ratio, it is RC, and RC is equal to V3 upon V2. V3 upon V2 we will look into more detail in the later part of the lecture. So let's first derive the thermal efficiency expression. We know that efficiency is equal to net work output divided by Q in. Net work output can also be written as Q in minus Q out. We can break the LCM. Q in will be cancelled out. 1 minus Q out upon Q in. So this will be expression number 1. Now Q in can be written as H3 minus H2, the enthalpy difference, because when we have a constant pressure heat addition, we can write as H3 minus H2, and H3 minus H2 can be replaced with MCP delta T, MCP T3 minus T2, and Q out will be similar to the Otto cycle, MCV T4 minus T1. So this is the main difference between Otto and diesel cycle. So in Q in was equal to MCV T3 minus T2, because in during constant pressure heat addition process there will be work done as well, there will be moving boundary work done, but in the Otto cycle when the volume was constant there was no moving boundary work done. Now this in the diesel cycle the moving boundary work during the process 2 to 3 can be combined in the internal energy formula. So internal energy plus moving boundary work is the enthalpy. So this thing we did in the thermodynamics course, so you can revise, you can go back and revise this thing. So that is why we have used H3 minus H2, and H3 minus H2 will be equal to MCP T3 minus T2. So we can replace Q in and Q out with these values. So 1 minus MCV T4 upon T1 Q out, MCP T3 minus T2 Q in. So M will be cancelled out. It can be written as Cp upon Cv in the division, and Cp upon Cv is K. So 1 minus T4 minus T1 K T3 minus T2. This is the equation number 1. Now what we can do, we can bring all the temperatures in term of compression ratio, cutoff ratio, and initial temperature. Then we can put the values here and then we can simplify. So let's start with process 1 to 2. So process 1 to 2, we can use the isentropic relation T2 upon T1 is equal to V1 upon V2 to the power k minus 1. So T2 will be equal to V1 upon V2 is R. So T2 will be equal to T1 R to the power k minus 1. So what we have done, we have represented T2 in terms of T1, R and K. Process 2 to 3, we can use the ideal gas relation P2 V2 divided by T2 is equal to P3 VT3 P3 V3 upon T3. Here P2 and P3 will be cancelled out because the heat addition process is constant heat addition process. So T3 upon T2 will be equal to V3 upon V2, and V3 upon V2 is actually RC, cutoff ratio. So T3 will be equal to T2 RC. Here we have defined the cutoff ratio. Now we can replace the T2 value from equation number 2. So T3 will be equal to T1 R to the power k minus 1 RC. So we have represented T3 in terms of T1 R, K and RC. Now we can apply the isentropic relation on process T3 to 4. T4 upon T3 will be equal to V3 upon V4 to the power k minus 1. Now V3 upon V4 can be written as V3 upon V2 multiplied by V2 upon V4. So we have multiplied and divided by V2. V3 upon V2 is RC. V2 upon V4, V4 is V1. V2 upon V1 is actually inverse of compression ratio. So 1 upon R. Here the formulas are written. So T4 is equal to T3 RC upon R to the power k minus 1, and we can replace the T3 value from equation number 4. So T3 is equal to T1 R to the power k minus 1 RC. From here R to the power k minus 1, R to the power k minus 1 will be cancelled out. RC and RC to the power k minus 1, their base is same, so we can add them together. So it will become RC minus 1 plus 1 will be cancelled out, RC to the power k. So T4 is also represented in terms of T1, RC and K. Now we can put the values of T2, T3 and T4 from equation 2, 4 and 6 in equation number 1. Equation number 1 was this. So we can put the values. Now we can take T1 common, and so T1 will be cancelled out from numerator and denominator. Then we will be left with RC to the power k minus 1, R to the power k minus 1, RC to the power minus 1. So this will be the formula for the efficiency of efficiency. So if you remember, the efficiency formula for the Otto cycle was 1 minus 1 1 upon 1 or r to the power k minus 1. So this formula is different by only this parameter. So 1 minus 1 upon r to the power k minus 1 is multiplied with this factor. We can call it factor a, let's suppose. So now factor a is RC, which is always positive and greater than 1. K is always positive and greater than 1. K is always positive, which is greater than. So this factor a will always be greater than 1. So what we are doing, that we are multiplying with a factor a which is greater than 1 to 1 upon r to the power k minus 1. Then this value, the net value, will be subtracted from 1. So now if we look at the formula of the Otto efficiency of the Otto engine, this is 1 minus 1 upon r to the power k minus 1. Now if I multiply with a factor a, then this value will come out to be larger than the previous value, and if we subtract a larger value from 1, then a smaller value will come out. So we can conclude that the efficiency for the same values of compression ratio, the efficiency of Otto cycle will be greater than efficiency of diesel cycle. Efficiency of Otto cycle will be greater than efficiency of diesel cycle at same compression ratio values. This conclusion will be valid because you can see that in the diesel efficiency we are multiplying 1 upon r to the power k minus 1 with a factor a. This factor is always greater than 1. So 1 upon r to the power k minus 1, a will be a greater value, a larger value, and if we subtract a larger value from 1, a smaller value will come out. So diesel efficiency will be lower than the efficiency of Otto engine. But this is happening at a constant compression ratio values, but we know that we operate a diesel engine at high values of compression ratio. That is why the diesel engines have practically speaking, the diesel engines have higher efficiencies as compared to the auto cycle, because only because of the reason that diesel cycles are operated at a very high values of compression ratio, because we do not normally observe the problem of knocking in the diesel engine, because we are compressing only air, and then we inject the fuel into the hot air. So we do not observe the problem of knocking as compared to the Otto cycle. So here we have mentioned that SI engines are operated at a compression ratio of 6 to 10, while diesel engines are operated at a compression ratio of 16 to 20, at much higher values of compression ratio. And in the last lecture, we saw that the efficiency graph is like this. So efficiency increases with the increasing values of compression ratio. So diesel engines are lie here and auto engines lie here. So they have lower efficiency than the diesel engines. But if we look at the mathematical formulas, then at same values of R, auto engines have greater efficiency as compared to the diesel engine. Okay, now let's do the derivation for the net work output. So this thing I have shown here. So now so if we look at the PV diagram of the diesel engine, so 3 to 4 will be area under the process curve 3 to 4, and this is the work output. Area under the process curve 1 to 2 will be work in, and there will be an additional work done during the process curve 2 to 3, because 2 to 3 is constant pressure heat addition process, and some work will also be done during the process 2 to 3 because it's a constant pressure heat addition. So we know that we will have some moving boundary work when we have a constant pressure process, which because P2 is equal to P3, we can write P2 V3 minus V2. So if you remember from the thermodynamics, for a constant pressure process, the formula for the moving boundary work is integration of P dV. And if pressure is constant, you can take P out of the integration and integrate volume with respect. The integration of dV will be V. Apply the limits, it will be V2 minus V1. So we have used the same formula here. So P2 is the pressure constant, V3 minus V2. V3 is the final volume, V2 is the initial volume. Then P3 V3 minus P4 V4 divided by K minus 1. This is the process. This is the work done during process curve 3 to 4. P2 V2 minus P1 V1 divided by K minus 1. This is the work done during the process curve 1 to 2. Negative sign is for work in, positive sign is for work out. So this thing we have used here. Now V3 upon V2 is RC. R is V1 upon V2, where V1 is equal to V4. So V3 will be equal to RC V2, V1 will be equal to RV2, and V1 is equal to V4. And P2 is equal to P3 is constant. So we can use these values here. So what we can do in the first term, we have taken V2 common. So P2 V2 V3 upon V2 minus 1. So we have taken V2 common from this expression. Here what we have done, we have replaced V3 with RCV2, V3 is RCV2, and V4 is actually V1 RV2. So here we have replaced 4. Now here P2 V2 is left like this, it's not changed. Now, and for V1 we have replaced RV2. So then what we can do, uh, we can take V2 common, because V2 is occurring in every term, so we can take V2 common. So P2 V2 is V2 we have taken common, P2 K minus 1 we have taken LCM here. So K minus 1, if we take LCM, K minus 1 will come here, P2 K minus 1, and V3 minus V2 is actually RC. V3 upon V2 is RC minus 1, plus we have taken V2 common, so RC P3 minus V2 common, R P4 minus P2 minus P1 R V2 common. So now what we can do now, we can do from here, we can take so P3 common RC minus P4 upon P3 R, and if we take P2 common from here, P2, we take P2, P2 will be cancelled out, or P2 taken common, 1 minus P1 upon P2 into R. Now P1 upon P2 is V2 upon V1 to the power K. V2 upon V1 is inverse of compression ratio 1 upon R. So P1 upon P2 will be R to the power minus K. P4 upon P3 will be equal to V3 upon V4. We can multiply and divide by V2. V3 upon V2 multiply by V2 upon V4. V4 is equal to V1. V3 upon V2 is RC. V2 upon V1 is compression ratio inverse. So it will become RC to the power K, R to the power minus K. And P2 is equal to P3 is equal to P2. So we can replace these values. So P4 upon P3, instead of P4 upon P3 power K, R to the power minus K, and instead of P1 upon P2, R to the power minus K. So we have replaced the values. Um, then what we can see, P2 is occurring in every trunk. So we can take P2 common as well. So P2 V2 K minus 1 RC minus 1 plus RC minus RC to the power K R to the power. Here we can see that R to the power minus K and R, their base is same, so it will become R 1 minus K. Similarly, R into R to the power K minus 1, it will become R 1 minus K. So their base is same, we can add the powers together. So now what we can do, we can multiply uh, K minus 1 to RC minus 1. So K into RC minus 1 minus 1 into RC minus 1. So minus RC plus 1. Similarly, we can expand here, minus plus minus plus RC plus minus will be cancelled out, plus 1 minus 1 will be cancelled out. We will be left with this expression, and we can take common from R1 minus K, R1 minus K we can take common. So we will be left with RC to the power K minus 1, because we have taken minus R to the power minus 1 minus R1 minus K common. Similarly, V2 upon V1 is inverse of compression ratio 1 upon R. So V2 upon V1 will be R minus 1. V2 will be equal to V1 R minus 1. So we can replace V2 here, V1 R minus 1. P2 upon P1 is equal to V1 upon V2 to the power K, R to the power K. So P2 will be equal to P1 R to the power K. So we can replace V2 and P2 here. So P2 V2 will be equal to P1 V1 R to the power K, R to the power minus 1. V1 P1 P1 V1 R to the power K, R to the power minus 1. You can see here. And R K to the power R minus 1, base same, power will be added, R K minus 1. So we can replace P2 V2 with P1 V1 R to the power K minus 1 in this expression. So we have derived the simplified expression for the net work of the diesel cycle. Similarly, mean effective pressure is work output divided by sweat volume. Work output we have just derived. Sweat volume is V1 minus V2. We can write V1 minus V2 as V1 minus V1 upon R. We have replaced V2 with V1 upon R. We can take V1 common. So P1 V1 and V1 will be cancelled out. 1 minus 1 upon R. We can take LCM, and then R will go. R will come here. So P1 R divided by K minus 1 R minus 1. So this is the expression for the mean effective pressure. Okay, so now we will solve few numericals. Let's start with question number 3.12. This is the unsolved numerical of book Sangil or book Garrison, or maybe the solved example, I guess. Determine the ideal efficiency of diesel engine having a bore of 250 mm, D is 0.25 meter, and stroke of 375 mm. L is 0.375 meter, and a clearance volume of 1500 cc with fuel cut off occurring at 5% of the stroke. Assume K is equal to 1.4. This is a very important statement. Fuel cut off occurring at 5% of the stroke. Now what does it mean? We will look in when we solve the numerical. So this is the solution of the numerical. we need to find the efficiency. Data is given. So since stroke is given, bore is given, we can easily calculate the swept volume with the formula pi by 4 d square into L. Swept volume we have just calculated, clearance volume is given, so we can easily calculate the compression ratio with this formula 1 plus Vs upon Vc. Uh, Here we have used Vs and Vc in meter cube, so R is coming out to be 13.27. Now if we look at the formula of diesel efficiency, so we need R, we need K, we also need RC, cutoff ratio. So we know R, we know K, we need to know the cutoff ratio. So for cutoff ratio, this statement is given: fuel cutoff occurring at 5% of the stroke. So what we can write, cutoff volume, we can write V3 minus V2 is equal to 0.05 swept volume. Now how do we get this? Uh, Let me show you here. Okay, so they are saying that fuel cutoff, that is fuel cutoff will occur at zero point 0.3 and fuel injection will be started at 0.2. So 0.2 fuel injection will be started, 0.3 fuel cutoff will take place. So V3, that is volume at V3, that is volume at 0.3 will be equal to V2 plus something. If we need to know the volume at 0.3, so it will be volume at 2 plus something. Now for this, the statement is given that is fuel cutoff is occurring at 0.5% of the swept volume. So fuel cutoff will occur 0.05, that is 5% of the swept volume. Then we can get the 3. So V3 minus V2 can be written as 0.05 swept volume. Now what we can do, we can calculate V3 in terms of V2 or Vc, because V2 is equal to Vc. V2 is actually the volume at TDC, and volume at TDC is actually cutoff volume, clearance volume. So what we can do, V3 minus V2, V2 is Vc, 0.05, 12.27 Vc. So we can see from here, Vs will be equal to 1 minus R minus 1 into Vc. R minus 1 will be 12.27. Here we have used 12.27 into Vc. So we have calculated V3 in terms of Vc. Ratio is V3 upon V2. V2 is Vc, so Vc will be cancelled out. So we have calculated cutoff ratio. Now we know compression ratio, cutoff ratio, K, so we can easily calculate the diesel efficiency from this formula. Now let's solve second numerical. A diesel engine is working with a compression ratio of 15 and expansion ratio of 10. Calculate the air standard efficiency of the cycle. So what is the compression ratio and what is the expansion ratio? So we can see from this diagram. So compression ratio is V2 upon V1 and expansion ratio will be between process 3 to 4. So V4 upon V3 will be the expansion ratio. Volume at 4 divided by volume at 3, because volume at 4 will be greater than volume at 3. So expansion ratio will be V4 upon V3. So compression ratio is 15 given and expansion ratio is V4 upon V3. So we can write V4 upon V3 as V4 upon V2, V2 upon V3. We have multiplied with V2 and V2, multiply and divide with V2. So V4 is V1. So V1 upon V2 is actually R. V3 is inverse of cutoff ratio. So we can multiply and divide by V2. So V4 is actually V1 and we can also write this thing as V3 upon V2. So V1 upon V2 is R and V3 upon V2 is RC, cutoff ratio. So we know the compression ratio, we know the expansion ratio, we know the compression ratio, we can calculate the cutoff ratio with this formula. So when we know the cutoff ratio, compression ratio and K values, we can use this formula and we can calculate the values for the thermal efficiency of diesel cycle. Let's solve another numerical. A diesel engine operating on the air standard diesel cycle has 6 cylinders. So K is 6 of 100 millimeter bore, D is 0.1 meter and 120 millimeter stroke. So L is 0.12 meter. The engine speed is 1800 rpm. At the beginning of compression, the pressure and temperature of air are 1.03 bar and 35 degrees Celsius. So P1 and T1 are given. If the clearance volume is 1 upon 8 of the stroke volume. So what does it mean? Clearance volume is 1 upon 8 of the swept volume. So we can use this relation to calculate the compression ratio. Calculate the pressure and temperature at the salient points of the cycle. That is, we have to calculate temperature and pressure at all the points, the compression ratio, the efficiency of the cycle, the power output if the air is heated to 1500 degrees Celsius. So uh, this is the temperature at point 3. Assume Cp and Cv. So we can start solving this numerical. We can convert 35 degrees Celsius to Kelvin by adding 273. So the initial part is very easy. R is equal to 1 plus Vs upon Vc. This is the formula for the compression ratio. Now we know that Vc is equal to 1 upon 8 into Vs. So Vs will be cancelled out. So the compression ratio will become 9. So with this statement we have calculated the compression ratio. Now next we can use the isentropic relations on process 1 to 2. P2 upon P1 is equal to V1 upon V2 to the power K. V1 upon V2 is R. R is known. P1 is given. So we can calculate P2, which is coming out to be 12.32 bar. T2 upon T1 will be equal to V1 upon V2 to the power K minus 1. V1 upon V2 is R. R is we just calculated and T1 is given, so we can calculate T2. Since we have calculated P2 and P2 will be equal to P3, so P3 will be calculated like this. P3 we have already calculated because P2 is equal to P3. Now we can use the ideal gas relation to calculate the cutoff ratio. P2 V2 upon T2 is equal to P3 V3 upon T3. P2 and P3 will be cancelled out, so it can be written as V3 upon V2 is equal to T3 upon T2. T3 is given, 1500 degrees Celsius was given. T2 we just calculated. V3 upon V2 is cutoff ratio, so RC is coming out to be 2.39. So compression ratio is V4 upon V3, and V4 upon V3 we just saw in the last numerical. V4 upon V3 can be written as V4 upon V2, V2 upon V3. V4 upon V2 is R, V2 upon V3 is RC. So we can calculate the compression ratio, which is V4 upon V3. Now we can again use the isentropic relations on the process curve 3 to 4. T3 upon T4 is equal to V4 upon V3 K minus 1, and V4 upon V3 we just calculated, it is expansion ratio. So you can also use directly RE 3.764 to the power K minus 1, which we saw that it is equal to 9 upon 2.39 to the power K minus 1. So T4 is coming out to be 1042.9 Kelvin. Similarly, we can calculate P4 3.49 bar. We can calculate Q in Cp T3 minus T2. Since T3 and T2 are known, we can calculate Q in. T4 and T1 are known, we can calculate Q out. Please students note that students always do mistake here in this step. They because sometimes they use Q in is equal to CV T3 minus T2. It cannot be, because we cannot use CV, because Q in is H3 minus H2, and H3 minus H2 is equal to CP delta T, not CV delta T. So once we know the Q out and Q in, we can calculate the diesel efficiency. The efficiency of diesel cycle 49.1%. We can, if we use the formula, this formula, we will get the same answer. If we use this formula of the efficiency, we will get the same answer. You can check. So power will be equal to work output multiplied by mass flow rate, because work output, you can see here, power unit will be kilojoule per second. Work output, it is in kilojoule per kilogram. So we need to multiply with kilogram per second. So kilogram will be cancelled out, kilojoule per second. So we need to calculate mass flow rate. So work output will be Q in minus Q out. Simple mass we can calculate, T1 V1 is equal to MT total mass, or MA RT1. R is Cp minus Cv 0.287. V1 is Vs plus Vc. We know that Vc is 1 upon 8 of Vs, so it will be 9 upon 8 Vs. Vs is pi by 4 d square into L, so we can calculate V1 with this formula. V1 is coming out to be 6.36 exponent minus 3 meter cube. Once we know the and we have multiplied with the number of cylinders as well, so to get the total volume. So V1, this is the important step. If we do not multiply with volume of one cylinder, so since it is, the number of cylinders are 6, so we need to multiply with 6. Now we know V1 P1 R T1, so we can calculate the mass. Mass is coming out to be 7.41 into exponent minus 3 kilogram. We need to multiply with N, because we want to convert, if we want to convert M into M dot, and M dot will have a unit of kilogram per second. So we need to multiply with small n, and n is equal to n by 2 for 4 stroke, and n is equal to n for 2 stroke. Now here you can see that n has a unit of RPM normally. We can convert it into RPS. So kilogram into revolution per second. So it will come out to be in kilogram per second. This thing we have done here. 1800 divided by 2 divided by 60 to bring it into revolution per second, and n by 2 is for 4 stroke engine. So mass flow rate is coming out to be 0.11 kilogram per second. So we can multiply the power with 0.11, so we can get the power output. 56.445 kilowatt is the power output of the engine. Let's solve the last numerical of today's lecture. A 6-cylinder 4-stroke. 6-cylinder means K is 6, 4-stroke means N is equal to capital N by 2, 4.5 liter compression ignition engine. So this is the swept volume is given. It is in liter dm cube. We can convert it into meter cube. Operates on the ideal diesel cycle with a compression ratio of 17. The air is at 95 kilopascal and 55 degrees Celsius at the beginning of the compression process. P1 and T1 are given. The engine speed is 2000 rpm. Capital N is given. The engine uses light diesel fuel with a heating value of 42,500 kJ per kilogram. CV is given, calorific value is given, an air fuel ratio of 24 is given, and a combustion efficiency of 98%. So we need to use this thing in the calculation of Q in, using constant specific heat at 850 Kelvin. So you can go to the property tables and note the Cp and Cv value at 850 Kelvin. We need to determine the maximum temperature in the cycle, that is T3, and cutoff ratio, that is RC. The net work output per cycle and thermal efficiency are required, the mean effective pressure, the net power output, the specific fuel consumption in gram per kilowatt hour. We need to calculate all these parameters. So I think it's similar to the numerical which we solved in the for the Otto cycle. So the start of the numerical is very easy. So at 850 Kelvin, the Cp, Cv, and R and K values are this. With the help of isentropic relation, we can calculate T2. Since T1 is given, compression ratio is given, and K we read it from the table. T2 is coming out to be 881.7 Kelvin. P2 we can similarly calculate, and P2 is coming out to be 4341 kilopascal. So now with the help of compression ratio and swept volume given, we can calculate the clearance volume. Clearance volume is actually equal to V2. The total volume will be equal to swept volume plus clearance volume, and total volume will be equal to V1. So we can add the swept volume and clearance volume to calculate V1. So we have calculated V2, V1, and now we can use V1 here. P1, V1 is equal to MRT1, M total. So if volume is total, so mass will be total. Total mass circulating in the closed loop. So T1 are known. V1 we just calculated, so we can calculate total mass. So once we know the total mass, we can calculate the mass of fuel with this air fuel ratio formula. Air fuel ratio will be equal to mass of air divided by mass of fuel. Mass of air can be written in terms of total mass minus mf. I told you in the last class as well that total mass will be equal to mass of fuel plus mass of air. So here we can write mass of air will be equal to mt minus mf. So we can calculate mass of fuel. Now this mass of fuel will be used. So we calculated V2, V1 and total mass to calculate the mass of fuel. Now the combustion efficiency is given. Combustion efficiency is 98%. It means that the energy released by burning fuel, 98% of that energy will be used, will be available as Q in. If the combustion efficiency is 100%, it means that all the energy by burning fuel will be available as a Q in, because the energy which we get by burning fuel will be added or supplied as a Q in to the working fluid circulating in the diesel cycle. Since the combustion efficiency is 98%, so combustion efficiency will be equal to Q in upon mf into Cv. This is the maximum heat which we are getting by burning fuel, the actual heat which we are supplying to the working fluid circulating in the diesel cycle, and this is 98%. So we need to multiply the energy we get by burning fuel with 9.98. So mf we just calculated, Cv was given, so Qin is coming out to be 8.039 kilojoule. Qin is known. Once Qin is known, T2 is known, T3 is coming out to be 2383 Kelvin, Cp is 1.110. Once we know the T3, we can calculate uh, the compression ratio, sorry, the cutoff ratio with the by applying the ideal gas relation on volume on process curve 2 to 3. P2 V2 divided by T2 is equal to P3 V3 upon T3. P2 and P3 will be cancelled out because it is a constant pressure heat addition, so P2 and P3 are same. T3 upon T2 will be equal to V3 upon V2, which is RC. T3 is known, T2 is known, we can calculate the cutoff ratio. Now V1 is equal to V4 and V2 is equal to Vc. And so we can calculate V3 with the formula. Similarly, P2 will be equal to P3. Now we can apply the process isentropic relation on the process curve 3 to 4. T4 upon T3 is equal to V3 upon V4 to the k minus 1. I think there is no need for this thing because it was for V3 and V4. V3 is this and V4 is this. We can directly put V3 is equal to 7.6 x1 minus 3 and V4 is equal to 4.781 x1 minus 3 here. There is no need to do these additional calculations. So T4 is coming out to be 1254 Kelvin. Similarly, we can calculate P4 with the isentropic relation. P4 upon P3 is equal to V3 upon V4 to the power K. P4 is coming out to be 363 kilopascal. So once we know the T4 and T1, we can calculate Q out. M total multiplied by CV T4 minus T1 Q out is coming out to be 3.677 kilojoule. Once we know the Q in and Q out, we can calculate W net, Q in minus Q out. Mean effective pressure will be W net divided by sweat volume. Sweat volume is known, work net is known. Similarly, power we can calculate by multiplying the W net has a unit of kilojoule. And if you remember in the Otto cycle numerical, it was in kilojoule per kilogram. That is why we had to multiply with the total mass. Since here it is already in kilojoule, so we do not need to multiply with the mass. Kilojoule multiplied by n upon 2. N upon 2 will have a unit of revolution per second, so it will become kilojoule per second, and kilojoule per second is power. Since it is a 4-stroke engine, we need to use n by 2. N is 2000 rpm, so we need to divide by 1000 to bring it into revolution per second. So power is 72.7 kilowatt. Specific fuel consumption we can calculate by dividing the mass of fuel with the net work output, and it will have a unit of kilogram per kilojoule. So we need in order to convert into a unit of gram per kilowatt hour, we need to multiply by 1000, because to convert kilogram into gram we need to multiply by 1000. Similarly, I already told you in the last class that we can convert the unit of kilogram per kilojoule into kilogram per kilowatt hour by multiplying by using this thing, because we can multiply and divide by second. So kilojoule per second will be kilowatt into second, and we can convert second into hour by multiplying with 3600. So that's all from today's lecture. So from this week lecture, what we have done in this week, we have done the uh, air standard Otto cycle and diesel cycle. We derived the expressions of thermal efficiency, net work output, and the mean effective pressure for Otto cycle and for air standard Otto cycle and diesel cycle. Then we solved few numericals. Students, I would like to answer one thing that few students have asked, that there are few things in the handout number 1 which we have not covered in the video lectures. So students, these things sooner or later will be covered in the other video lectures. So it's up to you. You can like, I remember in the handout number 1 there was a topic of uh, overhead cam engine and overhead valve engine. So we will cover this thing in the practical. So but if you want to learn by yourself, you can use the Google, and uh, you can learn about them, about what is the overhead cam engine and what is overhead valve engine, the difference between them, the comparison between them, advantages and disadvantages. You can easily learn with the help of Google. So a plenty of videos, a plenty of material is available. So like in the week 1 and week 2 lectures, I have included few videos, and thousands of these videos are available on the internet. So I recommend you, and my motivation of adding these videos was this, that I wanted to motivate you to keep on searching for the videos in the by yourself on the Google. Because let's suppose if you want to learn about the Otto cycle, there are plenty of videos are available for the derivation of thermal efficiency, network output, and mean effective pressure. There are some other videos available as well, because every teacher has its own way of explanation. So if you do not if you have not understood these things, maybe some other video lectures are available on the internet, or on the YouTube, or on the Google, which may have in a simple language, or a more much in a much uh, with much better explanation. So you are more than welcome to go through all these additional materials. So it will help you to understand and build the concepts. So I recommend you to keep watching different videos available on the internet. Some people have asked about the valve timing diagram. They have not understood well. So in the next live session, I will explain about the about the valve timing diagram. You can also search by You can also understand by searching, by watching different other videos available on the internet. So with this I end today's lecture, and this is the end of week 3 video lectures as well. See you next week. Allah Hafiz.